Okay, so welcome back to 719 Mathematical Economics. Today we continue our study on optimal control theory. So the last time we were just talking about the optimal growth example, right? So there's this capital stock and there's this consumption level, and the decision maker here maximizes something like this. So from t equal to 0 to positive infinity, right? To minus rho t dt. Okay, and the constraint is just there. So this is subject to kt dot equals kt to the alpha minus ct minus nkt. Okay, so labor force growth is modeled in this way. So when we look at the capital stock per worker, it obeys something like that. Okay. So what we shown was this, right? What we shown was this, and this dynamical system. So these equations already satisfy our three sets of conditions, right? So if you recall the first of the conditions, let me use a new one. So once again, this is the problem. This is subject to k0 greater than 0, right? And k dot equals kt alpha. So in general, it is fkt, obviously, minus ct and kt. And we studied this problem in this particular example, with the logarithmic utility function and with the Cobb-Douglas production function. Okay, so the current value Hamiltonian is something like this then, right? So we have ln CT, the current value is the shadow price. Then the constraint is this. So then we have first 1 over CT equals QT, right? Second, we have the constraint itself, kt alpha ct minus nkt. Third, we have the co-state equation, right? So this is the derivative of the Hamiltonian with respect to kt. So I have qt, and then I have alpha kt alpha minus 1 minus n, right? So then we realize that qt dot divided by qt is basically minus ct dot divided by ct, right? So the consumption growth rate is equal to minus the growth rate of the co-state variable. Right, so using these three things, we obtain the dynamical system. And then, of course, we are interested in the transversality condition. And now the transversality condition is this. Qt to the minus rho t, kt equals 0. Right? Now, let me go back to this figure. So we have this, so this is k dot t equals 0, and this is c dot t equals 0. And I told you that there is this saddle path, right? So on this saddle path, so once you arrive at the saddle path at some point, then eventually you converge to this. You converge to that point. So in these two regions, you behave in this way. In this region, you behave like that. In this region, your system moves like that. So now how to check the transversality condition? Once again, let me just rewrite it here. Qt e to the minus rho t kt. Okay. Well, in this steady state, you should realize that, so this is K star already, and we can denote it by C star, right? So remember how K star is found. So if I put the system here once again, I have something like this. Alpha kt alpha minus 1 minus rho plus n, right? And kt dot equals kt alpha minus ct minus nkt. So obviously, in this steady state, we have positive capital stock. So K star would be alpha rho plus n to the 1 over 1 minus alpha, right? So that one. And then you can find C star by plugging this into the K dot equals 0 equation. So C star will be simply K star to the alpha minus n times K star. Okay. Now realize one thing: the important property of a saddle path is this. In a dynamical system like this, if you are on the saddle path for some t, okay, then you never leave the saddle path. Okay, you converge to the steady state. That's the property of the saddle point equilibrium. All right. And if you are not in the saddle path for any t, if you are not exactly on the saddle path for any t, then you never go to the steady state. All right. So the movement of the system out of the saddle path, okay, is something like this. So in this region, you always go like this. All right. Here you always go like this. Okay. Here you always go like this. And here you always go like this. Okay. As long as you are on the saddle path, you have no trouble. You go to the steady state. That's a nice property of the saddle path equilibrium. And separately, you should normalize this system. Okay, now you have the steady state. So you can normalize the steady state, linearize the steady state, linearize this nonlinear dynamical system around this steady state point. Okay, so basically it will be something like this, right? The linearization of kt dot. And then you can move this point to the origin, so you can normalize the model. Then you can find the eigenvalues, and those eigenvalues will tell you under these conditions. So under if you have alpha between 0 and 1, n greater than 0, so these are the parameters of the model, and rho greater than 0, then you will find these eigenvalues to satisfy the saddle point equilibrium. Okay. Now the question is, what happens if we are not on the saddle path? right? If you are not on the saddle path, if you are not on the saddle path, let's say the saddle path is here, okay? If you are not on this, and suppose that we start here, so we will travel like this, and in this region, we're gonna travel like this, okay? So we will arrive at a point like this. And if we are here, we're gonna move like this, and eventually we're gonna travel somewhere here. Okay, if we are here, we're gonna move like this, and we'll travel somewhere here. Okay, and if we are here, it will be something like that. Okay. So now, of course, there are some problems with these points, right? This one, this one, this one, and this one. There are some, let me put some question marks. So what is the problem? So let's look at these first. So this is again CT and this is KT, right? The problem is this. Your budget constraint could be written in this way, right? So this is now a different way to write the same resource constraint. Now you have the total resource, your production, right? This is your total resource at T, depending on your state variable capital stock. Now you allocate this resource to three purposes, to three ends. One is consumption, the other is saving, and the other is depreciation, that is, labor dilution here, right? Now this will tell you, if you be a little bit more careful in interpreting what these variables are, this requires these non-negativity constraints, right? So you must have positive amount of capital if you want to consume, right? Because CT will be less than K2 to the alpha, right? K dot T will be less than K2 to the alpha, and KT will be less than K2 to the alpha. So this is our feasibility constraint, right? Typically, in the formulation of the problems, we do not write this because it is too obvious, right? But what happens in these points? These points violate the feasibility constraint, right? So these are feasibility constraints. And these points, this one and this one, they violate the feasibility constraints. Why? Because we want to consume a positive amount with no capital and no production. Okay? Now let's look at the other points. These ones. Well, what's happening here? Well, in those points, we have a lot of capital, right? But we consume 0. Now, from the logarithmic case, obviously, we already know that CT equals 0 is not optimal, but here we have a more general problem, right? I mean, this is true even if we do not have log utility, right? So what's going on here? The idea is this: those points, these points where capital stock is positive and consumption is 0, they violate the transversality constraint. Okay, here we accumulate too much capital, and even if it is valuable, we are not consuming it. All right. Now, how to show this? Now there is a proof in the website. If you check my website, wordpress.com, you're going to see the proof of it. But the idea is very simple. The transversality constraint is written in this way, right? So Qt is basically 1 over Ct, right? So limit, remember, Qt is 1 over Ct from the first to the condition. So I have actually Kt divided by Ct times e to the minus rho t. Now the steady state obviously satisfies this, right? Because in the steady state, you have K star divided by C star going out. It's just a positive number, right? And then you have this, and obviously this is equal to 0. All right? So the steady state satisfies the first of the condition. But guess what happens here? If Kt is positive, right? If Kt is positive, so here, in such a point, if Kt, so this is K star, C star, and this is another point, K hat. Now, in such a point, transversality condition is written in this way. K hat, a positive number going out, you have limit t going to positive infinity, you have e to the minus rho t divided by ct, right? And obviously, this is not 0, right? Regardless of how how fast consumption goes to 0, it doesn't really matter because consumption is already 0 there, right? So it is then violating the transversality constraint. Okay, this point. Why? I mean, the math is here. The economic logic is already there because we accumulate too much capital and we do not use it, which is not rational, which is not optimal, right? If we were not use it, if we were not to be use it, why we accumulated it? All right, that's the reasoning. So again, there is a formal proof that I shared in the website. I'm not going to go into that detail in the lecture, but this is the simplest possible example that you will see for the optimal control theory. You know, this is of course the economic model. Today we're going to see a couple more different problems. We can actually design new problems in the class. But the idea is this. There is this objective function. As a decision maker, my objective function is intertemporal. So I basically face dynamic trade-offs. Okay? If I use all my resources today for today's rewards, then I leave nothing for tomorrow. Okay? Of course, I wouldn't do that optimally in the optimal solution. I wouldn't do that because I will be caring for rewards in the future as well. So the idea is to allocate today's resources to today's consumption or today's rewards and future's rewards in an optimal way. Okay? Since there's a dynamic trade-off, the typical Lagrangian wouldn't work very easily. You can solve with this problem. You can just make sure you can solve this problem by Lagrange because this is just a mathematical optimization problem, but it is too cumbersome. Okay, Hamiltonian makes interpretation much more easier, and especially current value Hamiltonian makes the interpretation much more easier, much more clear. So we use the Hamiltonian approach. Okay. These conditions should be satisfied. Then I look at the second order conditions. Second order conditions are satisfied in this typical problem, for instance, right? Concavity properties. And in fact, I know that the optimal path is unique because natural logarithm is a strictly concave function. Remember the second order conditions. Second order conditions are like this. So F0 is concave, and Fi's are concave. This is good for optimum. If additionally F0 is strictly concave, right? Then you have uniqueness. Okay. So now it's a good point if you have any questions, because this is the main idea. We're going to apply the very same logic in different types of dynamic optimization problems. Again, each of the four first of the conditions have meanings that we discussed last week. You can, I mean, if you do not get the ideas, we can discuss them. At some point in a couple of years ago, you know, I completed our study in the class, our study of the optimal control theory in the class. After a couple of weeks later, some students told me that they didn't get the logic. So I don't want that. If you have questions, if I left something unclear up to this point, just let me know so we can cover it up, and then we continue with other examples. We have time. I can go over the material again, and then today I will show you many more different examples. Okay, so everybody's happy with my content then. So let me continue with another example. Okay, now I cannot share my screen. Okay, so the same optimal growth problem could be studied with, of course, alternative utility functions, right? And alternative production functions. So one example would be this so-called isoelastic utility function. For some epsilon greater than 0. There's another version of this function. Sometimes we write in this way. Okay. It's about basically risk aversion, but I mean, it doesn't really make a big difference for our purposes here. So if this is your utility function, the only part that changes is this. The first order derivative, the marginal utility, right, is now Ct to the minus epsilon, right? So if you equate this to Qt, right? So you have something like this: Q dot T equals minus epsilon C to the epsilon minus 1 C dot T, right? By the chain rule. So what do you have here? You have minus epsilon Ct to the minus epsilon Ct dot divided by Ct. Now realize that this is again Qt, right? So at the end, Qt dot divided by Qt is equal to minus epsilon Ct dot divided by Ct. Okay? So obviously, that makes a difference. And for this utility function, when epsilon converges to 1, this utility function converges to logarithmic utility. Then, of course, Q dot T divided by Qt converges to minus Ct divided by Ct dot divided by Ct, right? So this is just one different utility function, and it changes the relationship between cost state variable and consumption. Okay. Now, when we do that, we should also discuss what we call the Euler equation. Okay. Now recall this cost state equation. It was like Qt alpha kt alpha minus 1 minus rho plus n, right? Sorry, rho is already there, so it was like this. And now let's write this in a different way, okay? Let's write this for this utility function. Okay? So now I know that q dot t divided by qt is equal to minus epsilon c dot t divided by ct, right? So in other words, ct dot divided by ct is minus 1 over epsilon q dot t divided by qt. Okay? So from this equation, I have q dot t divided by qt equals minus alpha kt alpha minus 1 plus m plus rho.